Hello all, good evening. My name is Arjun Yadav, and we are here to discuss the two technical papers which we have got for group presentation video 3. And the main agenda for this meeting is to discuss about the comparative analysis of search algorithms. So here in this paper, we are discussing about the different search algorithms and the main drawbacks and the comparison of those and the applications of those algorithms. And in the second paper, we are having severe weather avoidances using informed heuristic search algorithms. And comparative search analysis of search algorithms, AI, as we know that this deals with the computer, like to produce a machine which thinks like a human being, and AI has like several search algorithms to solve this shortest to find the shortest path for the problems. AI, machine learning, and deep learning and data science are they're like very much interrelated subjects. In search algorithms, we have two different approaches. One is uninformed search algorithm, and the other is informed search algorithm. The first approach is uninformed search algorithm, which is having, it is a blind search algorithm or brute force search. The examples for the uninformed search algorithms are breadth first, depth first, and uniform cost search algorithms. In this, the information regarding the number of steps is like there is no information how we are reaching the goal state. And the other one is informed search algorithm. It is a heuristic search which use the functions, like specific functions to get the solutions for a particular problem. The examples for this type of approach is like A star, AO star, and best first search algorithms. Among these two, the informed search is more superior compared to the other one. These are the different search techniques we are going to discuss today. Breadth first, depth first, uniform cost, A star algorithm, and the last one is best first search algorithm. It's also called as greedy search. This is the first algorithm. This is breadth first. Here, this is the like simple example to demonstrate these algorithms. Here, the nodes are different nodes 1, 2, 3, 4, like till 8. 8 is the goal state which we are having, and we are starting from first, and we are reaching the goal state in different like layer. It is like the nodes are arranged in layers, and we are going by layer. It is almost it is similar to the first in, first out algorithm. This strategy is very poor because if we need to go to the goal state, we need to go through all the layers. Like by breadth, we are going down to the goal state. It is not utilized when memory is requirement is high. The best breadth first search is applicable when the problem consisting of least curves and it has multiple solutions which has short path length. When the problem has no memory constraint, we can apply this. The main applications are like unweighted graph minimum spanning tree and short path search. When we have shared network, we can use this, and website for social networking and global positioning. Depth first, this is the other one. I have taken the same example. It is almost similar to last in and first out search algorithm. It goes into the depth, like to reach the goal state, it will reach one, like the path, for example, 1, 2, 6, 9 to 8. It goes on like to depth. It is also known as a recursive algorithm. The depth first search is applicable when the memory is limited, when the graph is infinite. We need to apply this this search algorithm for those problems. And the main applications are graphs, when the graph, to identify the graphs in a loop and finding components of a graph which are tightly linked, and to find the solution for the riddles which have just one possible solution. And the other search algorithm is uniform cost search. This is like arranged in this, the source is at node 1 and the goal state is at node 12. And we do achieve the solution by using nodes at, which have low cost root. The cost function for this is C of given C of m is equal to C of n plus C of n comma n. Here C of m is the cost current node, C of n is the cost of previous node. And here it is a combination of the resultant will be the combination of previous nodes and the functions of n comma n. It almost calculates the weights in sequence to reach the goal state. The uniform cost search, it is applicable when the space requirement is less, and the intelligence, if we don't want the intelligence to get the solution, we apply this type of algorithm. And the main applications of this uniform cost search algorithm is to solve maze problems and to find the path. A star algorithm is similar to the previous one. It combines the best features of uniform cost search and pure heuristic search to get optimal solution. The cost function is f of m is equal to C of m plus h of m. Here C of m is equal to C of n plus C of n comma n. This is like the combination of the previous one and the heuristic function. It is applicable. The applications are applications of this algorithm are systems for navigating the traffic and to having games to develop the games and identifying the shortest path and real-time path replanning techniques. Best first search algorithm is also known as greedy search algorithm. It is a mix-up of both breadth first and depth first. It follows the rule of both to find the best solution. At each step, the best suited node among the produced one is picked for assisting expansion. It do expand on the previous node's feedback, and it goes whenever it is required, it goes into depth, or else to find the optimal solution, it may choose the breadth search also. It is also referred as greedy search because it shortens the path by analyzing itself. And the main applications for this are games, to develop the games, and web crawlers. This is the way we compare the five previously discussed algorithms. Time complexity, space complexity, optimality, and completeness are the deciding factors to choose the best algorithm which suits for us. Time complexity is defined as the time which the algorithm takes to give the best solution or else to reach the goal state, and space complexity, how much space it needs to finish the problem, and the optimality, whether we can achieve the optimal results or not. For example, unified cost search algorithm, the third one, the optimality is yes. That means it will give an optimal solution. In the same for the other algorithm, DFS, depth first, we don't reach the optimality to find the solution. And the completeness is how we get the computational problem by using these search algorithms. These are the this is the way we compare the algorithms. By this, according to the application and our need, we need to select the algorithm which suits for the problem. To conclude, we have blind search is less efficient and acceptable than heuristic search algorithm, and uniform cost search requires a great number of nodes compared to A star to reach goal state. And breadth first search is more optimal because it expands shallowest unexpanded nodes every time. That's where I conclude, and Chase will continue for the next. Thank you.
Hello, everyone. My name is Chase Sheldon. I'll be going over the next article, which is severe weather avoidance using informed heuristic search. In aviation, severe weather is a major safety and logistical concern. During thunderstorms, aircrafts must find a way to avoid the dangerous conditions by finding a different route. It is almost never possible or allowed for a pilot to fly an aircraft through severe weather. In this article, it was discussed how an algorithm was developed in order to find the minimum cost path around the thunderstorm. This is done by using a radar to detect a thunderstorm as input and using the A-star search algorithm with some key modifications. The A-star algorithm is an informed search technique that was used to evaluate the total path cost of avoidance at any given point. We will discuss how the algorithm was formulated and how it has been shown to work in some cases. Next slide. Airplanes spend most of their operation time in the sky. Over 20% of all aviation accidents are a result of severe weather. For this reason, significant weather is a primary concern for aviation. To deal with this issue, it is important to understand the weather and its effects. Since the concept of free flight has emerged, this has become even more important. Free flight is a system that manages air traffic. It allows pilots to have more control over flight routes. This extra flexibility begins at the end of the departure sequence and ends at airport arrival sequencing. With the use of free flight, it's even more important for pilots to have help from algorithm to guide them in the changing weather. Next slide. One algorithm that has sought to help with the shortest path algorithm is the Dijkstra. This helps in some cases to provide a simple method of determining the shortest path around a severe storm. This algorithm can show the shortest route, however, it comes short when trying to find the most desirable route. Another algorithm is the A-star search. This search is designed to give an adaptable route. It has been used to find the desirable path around a thunderstorm that has arisen on the original flight path. The heuristic function has two components. The first is a consideration of the cost between the moving from the starting point to a point that is being considered. The second is moving from the point considered to the end of the route. After this, the principle of the A-star search algorithm is used to determine the best path. Next slide. Severe weather is any weather phenomenon that is destructive. This seems like a broad generalization. However, it can really be thought of as any localized storm. Typically, this includes weather that has strong wind, violent updrafts and downdrafts, and heavy precipitation. All of these factors can cause damage to an aircraft and cause a pilot to lose control. The typical data needed by a pilot regarding weather is radar reflectivity, wind speeds and direction, turbulence, icing severity, and temperature. In the radar image that you can see here, a 2D Gaussian function shows the weather severity of a thunderstorm. To get this image, computations were carried out to accurately represent the severity. A safe flight path is considered to be any region with an intensity rating of less than 30 decibels. Any level greater than this should be avoided. In the image, the blue, green, and empty areas are safe for travel. Any image that is computed as shown and all the intensity factors of what is considered by algorithm when looking for the ideal flight path. Next slide. A heuristic search is a search that looks for a solution space for an optimal solution into a particular problem. A-star search is an informed heuristic search. The purpose of this search is to minimize the total cost path. At every node, the function f is evaluated. This function consists of two parts. G is the actual cost of reaching a node, n, and h is the heuristic function that estimates the cost of node n to the goal state. At each level of the search, the node that is deemed to have the lowest function value is expanded. The ideal effectiveness of the heuristic function is when the cost of reaching a particular node is never overestimated. In this case, if this is the case, then the search can be shown to be optimal. If a best solution exists, then this technique will be able to find it. This is a huge advantage to using this technique over others. The downside is that this technique requires a lot of time and memory since all generated nodes are stored. There are, however, some modifications that can be done to improve the speed. Next up is Nagasai, and he'll be continuing our talk of this article.
Hey guys, I'll be continuing what Chase have started. It's the same paper, research paper, the severe weather avoidance using informed heuristic search. So the A-star search algorithm was discussed by Chase. We'll be going through the other other possible algorithms. Can we go to the next slide, Arjun? Yeah. So to develop the weather avoidance algorithm, there are certain constraints which we need to consider. Those are minimum segment length, maximum turning angle, and minimum number of turns. So coming to minimum segment length, it is basically between any 2 points on the flight path, the distance between them should be greater than or equal to certain minimum distance. In order to make this pilot job easier, this is actually needed. So also the plane should be able to finish one turn before starting another one. So that is a minimum segment length. So coming to maximum turning angle, people who fly usually makes a turn that changes their direction less than 60 degrees. In any case, the changes should not be more than 90 degrees. So that's a maximum turning angle constraint. Minimum number of turns is something that the produced flight route should be a piece of linear and contains a very few tests as feasible. This is necessary to elevate the pilot's strain. So these are the constraints. These are considered while actually developing the heuristic function on this process of developing the algorithm. Can we go to the next slide? So in the thunderstorm avoidance algorithm, so there was a figure which was given. So in this figure, there are a couple of things which were explained. So here, the A-star search algorithm is actually made few of the modifications in accordance with the simplified memory bounded, which is SMA star method, which is actually derived from A-star search algorithm. So in coming to the figure, so nodes actually will be chosen along the lines. Suppose a node with a depth 1 is between the points 1 and 2. If you take a path through this node, it will never be the shortest. Hence, the nodes between the 1 and 2 should be removed to cut down on the number of calculations that need to be done. The number of nodes that can be at each stage is actually limited. So this is how it actually works. A thunderstorm doesn't have any starting point or an ending point. If they aren't, then in the search tree, the root node is the starting node and the terminal node is the ending node. So in this algorithm, we assume that thunderstorm in front of a plane as it flies, and that neither of its 2 points, which are start and end points, are in the area that isn't open to us. So the A-star algorithm is modified, as said, and the simplified memory bounded A-star SMA star algorithm is done. So there is a downside to SMA star search algorithm. If a memory is allocated less than the memory necessary for the best part to the destination node, the search method will either return a suboptimal solution, or in worst case, there will be no solution at all. Can we go to the next one? So the paper also discussed results of application of these specific algorithms which were developed on specific data set, which they have a radar picture of stationary thunderstorm. So in the figure 4, that's the first situation. The beginning and the end points are clearly visible, as in the thunderstorm that sits in the flight route. There is an inaccessible area, which is calculated using the definitions which were mentioned in the earlier portions of the presentation. So the gray area in this figure 5 corresponds to inaccessible area. In the figure 4, there is a point 1 and a point 2. Point 1 is considered as starting point and point 2 is considered as ending point. So after tracing the whole inaccessible area, there is a technique which applies on top of it, so that the shortest flying path between 1 and 2 is determined, that actually avoids the thunderstorm. So in this figure 6, the flight route in relation to inaccessible locations, where figure 7 actually illustrates the flight path in conjunction with the radar image. In this situation, the minimum segment length on the radar picture is 8 units. So there is another example where it is considered in the figure 8, where it depicts the stationary thunderstorm that is there in the flight path as indicated in the picture. The initial flight route from point 1 to point 2 passes through a thunderstorm, and the flight route actually depicted in the graphic is one dictated by the weather storm avoidance algorithm. So in the case 2, there is nothing but a figure 8. The minimum segment length is actually 10 units. So while performing this algorithm on a Pentium 2 PC, it actually took 11.1 seconds to compute the safest path. So in the case of in case 3, that is figure 9, so there are 3 line stationary thunderstorm exist in the initial flight path. Can we go to the next one? Yeah. So there are other 2 figures which were given, that is 10 and 11, which also shows the results, and these cases are considered as 4 and 5. So basically the radar picture is given in a different format that they call it as contour map, which doesn't have a map, doesn't have a grids. In all other cases earlier there were grids. So in this case 4, there was a line of three thunderstorms, as we mentioned. So they were traveling on 40 miles per hour rate in a positive x direction. So any airplane which is traveling on a constant speed of 150 knots between a point 1 and 2, point 1 is considered as starting point and point 2 is considered as the ending point. So basically the figure 10 actually depicts the airplane's safe course in that instance to avoid the thunderstorms. As you see, it's kind of tangential. So in the case 5, there's a line of thunderstorms. So it's something like similar to their line, like a square line. So they are traveling 50 miles per hour in a negative x direction. So the figure 11 actually denotes the beginning of 2 endpoints. So it's the same thing, like point 1 is considered as a starting point and point 2 is considered as a ending point. So the airplane's real safe route has been marked there. Can we go to the next one? So although these algorithms were applied, there are few limitations to these algorithms. They are considered as there is no actually safe diversions which are estimated by these algorithms, because a beginning route of the area is very high levels. So if the beginning route of the area has a very high level of thunderstorm activity, the algorithm continues to fail giving the proper route. So the algorithm itself is trying to discover solutions if they are trying to go on a forward direction, being flanked by the thunderstorms. And try to retrace the whole path which actually moves away from the thunderstorm. So for now, we don't know like how well the algorithm works on a large sample area, but from all the results, it actually works well in the smaller areas. So the shorter routes can be made by making the grid smaller, but it can make the algorithm too slow. Can we go to the next slide? So coming to the conclusion of the paper, algorithm was developed for general aviation. So the algorithm is essentially based out of A-star search algorithm, and suitable changes were made to made to the A-star algorithm, develop the SMA star search algorithm approach, which actually lowers the time and space approach. So in this SMA star algorithm, what actually happens was explained in the sense, whenever the memory is run out, new memory is allocated and the highest costly function is been removed. That was actually explained properly in this paper. The findings of these algorithms is correctly computes the safest and the shortest path in the limited region of the map. So the results are also been shown in this paper. Can we go to the next slide? So coming to the conclusion of the whole presentation, as Arjuna explained, the paper 1 has discussed and compared performance parameters of different search algorithms and also discussed their applications and drawbacks. Coming to the second paper conclusion, in the general aviation industry, a severe weather avoidance algorithm has been discussed, which actually is based out of A-star search concept. There were few changes which have been done to the A-star search concept, and SMA star search approach has been introduced to which actually minimizes the time and the space requirements. That's all. Thank you, guys.